This video is about Pascal's triangle and the binomial theorem. So you've likely seen Pascal's triangle before. Pascal's triangle starts with a 1, and then a 1, 1, and then 1, 2, 1, 1, 3, 3, 1. And you may have, or there is a pattern for Pascal's triangle. Every row of Pascal's triangle begins and ends with a 1, and all the other entries of the triangle can be found by adding the two values above to get the value below. So 1 is 2, 1 and 2 is 3, and so on. So this entry will be 1 plus 3 is 4. This entry will be a 6. This entry will be a 4. And again, we end the row with a 1. So now we're going to discuss the relationship between the entries of Pascal's triangle and n choose k. Recall that we also wrote n choose k as n choose k, and that n choose k is the number of ways to select k objects from n objects where order does not matter and repeats are not allowed. So the relationship is that if we start counting with 0 instead of 1, then the kth entry of the nth row of Pascal's triangle is n choose k. So in Pascal's triangle, this is row 0, this is row 1, row 2, row 3. And so this entry, for example, would be the 0, 1, 2. So 3 is the second entry of row 3, again starting our counting with 0 in both cases. And so according to this claim, 3 should be equal to n choose k. N is the row number, k is the entry number, so 3 choose 2. Let's verify that. So 3 choose 2 is equal to 3 factorial divided by 3 minus 2 factorial times 2 factorial. So that's 3 times 2 times 1 divided by 3 minus 2 is 1 times 2 factorial is 2 times 1. So yes, we are left with 3, and in this case, the claim is true. We want to show that this relationship is always true. So there are two rules that build Pascal's triangle. The first is that every row begins with a 1 and ends with a 1. So all of the first entries are 1 and all of the last entries are 1. And the second rule is that each of the middle entries are given by adding the two values above. So any middle entry is given by adding the two values above. Let's start by showing that the first property is true. So each row begins and ends with a 1. If it's true that the kth entry of the nth row is n choose k, then this should be 0 choose 0. This should be 1 choose 0. This should be 2 choose 0, and so on. And this entry should be 1 choose 1. This entry should be 2 choose 2. This entry should be 3 choose 3, and so on. So to show that the first property is true, what we need to show is that to show that the first entry of every row is 1, we need to show that n choose 0 is always 1. And to show that the second part of that is true, we need to show that n choose n, the last entry of every row, is also 1. One way that we can do that is with the formula for n choose k. We know that the formula for n choose k is n factorial divided by n minus k factorial times k factorial. So what is n choose 0? N choose 0 is n factorial divided by n minus 0 factorial times 0 factorial. So that's n factorial divided by n minus 0 is just n factorial times 0 factorial. 0 factorial is 1. And so we're left with n factorial divided by n factorial, which is 1. So great, we have just shown that this is true. To show that n choose n is equal to 1, we can do the same thing. So this is n factorial divided by n minus n factorial times n factorial. So that's n factorial divided by n minus n is 0 factorial times n factorial. So we'd be left with n factorial divided by, again, 0 factorial is 1 times n factorial. And so this reduces down to 1, and we've shown that this is true as well. An alternative way to show this is to consider the definition of n choose k, that n choose k is the number of ways to select k objects from n objects where order doesn't matter and repeats are not allowed. So if we think about n choose 0, that's the number of ways to select 0 objects from n objects. So if I have 10 cards sitting in front of me on the table, how many ways are there for me to pick none of them up? There is one way for me to pick none of them up. Similarly, if there are 10 cards sitting on the table, in how many ways can I pick all 10 of them up, where the order in which I select them doesn't matter, and I can't repeatedly pick up the same one? Well, there's only one way to do that. I just scoop up all 10 of them, or the order in which I'm taking those 10 does not matter, so there's only one way to do that as well. So that's another way to show that n choose 0 is 1 and n choose n is 1 for all non-negative integers n. Now we want to show that the second building block of Pascal's triangle is true, that each middle entry is given by adding the two values above it. For any values of n and k, this would correspond to, if we take the nth row and the entry before in that row, plus the nth row and the next entry in that row, that should be equal to the entry in the row below, so in the n plus 1th row, and then it will be the kth value in that row. So for example, if we look at these values, this would be the third row, so n would be equal to 3, and this should be the kth entry, so k is also 0, 1, 2, 3. K is also equal to 3, and so what this identity is saying is that 3, n is 3, choose k minus 1 is 2, plus 3 choose 3 should be equal to n plus 1, that's 4, choose k is 3. And we could verify that. So 3 choose 2, that is equal to 3 factorial divided by 3 minus 2 factorial times 2 factorial, which simplifies down to 3, plus 3 choose 3, we already know is 1 because n choose n is always 1. So this is 1, is equal to 4 choose 3. 4 choose 3 is 4 factorial divided by 4 minus 3 factorial times 3 factorial. So that's 4 times 3 times 2 times 1 divided by 4 minus 3 is 1 factorial, which is just 1, times 3 factorial, 3 times 2 times 1, cancel, cancel, and so yes, 3 plus 1 is equal to 4. Great. So one way to show that this identity is always true is to use the formula for n choose k and simplify the left-hand side and show that it will end up being equal to the right-hand side. So what's n choose k minus 1? N choose k minus 1 is n factorial divided by n minus k minus 1 factorial. So n minus k minus 1 factorial. So anywhere we see a k, we're instead sticking in a k minus 1. So also multiplied by k minus 1 factorial plus n choose k. We know what n choose k is. That's just n factorial divided by n minus k factorial times k factorial. So we can continue to simplify that. So this is n factorial divided by n minus k minus a negative 1, so distributing the negative gives plus 1 factorial, times k minus 1 factorial, plus n factorial divided by n minus k factorial times k factorial. So far, this is just the left-hand side of this equation written out. So to add these two fractions, we need to find a common denominator. So if we want to find a common denominator, let's look at some things that are kind of similar. So in the denominator, on the left-hand side, we have a k minus 1 factorial, and on the right-hand side, we have a k factorial. So what's the relationship between those two? Well, k factorial is k times k minus 1 times k minus 2 times blah, 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 down to 1. And we can see that that's actually equal to k times k minus 1, k minus 2, dot, dot, dot. That's just k minus 1 factorial. So what we could do is multiply this by k, and if we multiply this by k, those two would be equal. So let's multiply the numerator and the denominator of this by k to start to get a common denominator. And similarly, let's compare n minus k plus 1 factorial to n minus k factorial in the two denominators. So again, we want to get a common denominator. What can we multiply by to achieve this? So we can use the same trick. So n minus k plus 1 factorial is the same thing as n minus k plus 1 times n minus k times n minus k minus 1, dot, 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 all the way down to 1. So what is this? This is just n minus k plus 1 times n minus k factorial. And so we see that what is missing from n minus k factorial is multiplying by n minus k plus 1. And that would make those two quantities equal. So we can multiply the numerator and the denominator of this fraction by n minus k plus 1, n minus k plus 1. And so the quantity above simplifies to k times n factorial divided by n minus k plus 1 factorial times k minus 1 factorial is just k factorial, plus in the numerator n factorial times n minus k plus 1 divided by n minus k factorial times n minus k plus 1 is n minus k plus 1 factorial times k factorial. Now we've got a common denominator, so we can add those two fractions together. We leave the denominator alone, n minus k plus 1 factorial times k factorial. And then the numerator is now k times n factorial, or n factorial times k, plus n factorial times n minus k plus 1. So there's an n factorial in both terms in the numerator, so we can factor that out. So the numerator is n factorial times k plus n factorial is also multiplied by n minus k plus 1 divided by same denominator, n minus k plus 1 factorial times k factorial. Now that is equal to n factorial times, we can simplify up in the top, so the k's cancel out with each other, and now we've got n plus 1 divided by n minus k plus 1 factorial times k factorial. So we can now simplify the numerator a bit. So we have n factorial times n plus 1. Well, that's n plus 1 times n factorial. So n factorial is n times n minus 1 times n minus 2 times dot, 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 down to 1. So what is that? This is just n plus 1 factorial because it's n plus 1 times every positive integer less than n plus 1. So we can simplify the numerator to n plus 1 factorial divided by n minus k plus 1 factorial times k factorial, which is equal to n plus 1 factorial divided by, just rearranging, n plus 1 minus k factorial times k factorial. And what is that? That is n plus 1 choose k. It is n plus 1 factorial on the top divided by n plus 1 minus k factorial times k factorial. So that is the formula for n plus 1 choose k. Okay, so that was a lot of algebra, but we just showed this, that n choose k minus 1 plus n choose k is equal to n plus 1 choose k. And so that is great because we've shown something pretty cool. We've shown that the kth entry of the nth row of Pascal's triangle is n choose k, starting counting with 0 instead of 1. Why? We showed that each of the first and last entries of every row are 1s forever because n choose 0 is always 1 and n choose n is always 1. And then how can you prove that the remainder of the entries also correspond to Pascal's triangle? Well, we've basically done it inductively. If you take any two entries, n choose k minus 1 and n choose k, we can get the next entry, n plus 1 choose k, by adding the two entries above. And so yes, we have shown that every entry of Pascal's triangle corresponds to n choose k.